So we are going to do the time and frequency response analysis of a first order system. So an RC circuit is used as a first order system here. You can see a resistance and a capacitance connected in series, and we will apply the input to this particular port. Ei of t is the input signal, and the output is measured across the capacitor, that is E of t, E0 of t. Then the time constant of the circuit is assumed to be equal to 0.1 millisecond. So time constant of this simple RC circuit is R multiplied by C, and we are taking it as 0.1 millisecond. So for R equal to 1 kilo ohm, you will get C is equal to 0.1 microfarad. So these are the component values that we are using: R equal to 1 kilo ohm and C equal to 0.1 microfarad. And this circuit is wired up here in a breadboard. So 1 kilo ohm resistance is placed here, and this is C, capacitance of 0.1 microfarad value, and they are connected in series. And we will use a function generator to give the input signal. And first we have to apply a step input to this particular port to obtain the step response of this first order system. But in our lab we don't have step signal available in the function generator, so a low frequency square wave is used instead of step signal. So a function generator is here, and we will take a square wave signal of low frequency, say 100 Hz, from the function generator, and that is connected to the input port of this circuit across R and C, and output is available across the capacitor, and that is that we will observe that output signal in the CRO. So I have connected both the input as well as output signals to two channels of the oscilloscope. In channel 1 we have connected the input signal, and in channel 2 the output is given. So here you can observe the square wave signal given to the input port. Okay, so if I change the time per division, you can see that this is similar to a step signal. If you observe this particular duration, this is much larger compared to the time constant of the circuit. So for this particular circuit, this will appear as a step signal because time constant is only 0.1 millisecond, and this is much larger than 0.1 millisecond for this particular time per division. So this is acting as a step signal, and you can observe the output here. So output I have connected to the other channel. So the first order response, that is exponential rise of the output, you can observe here. Okay, so this output will reach 63.2% of its nominal value at 0.1, around 0.1 millisecond. So experimentally also you can measure what is the time constant of this particular circuit from this plot. Okay, that is about the time response of first order system. Next we will do the frequency response analysis of this first order system. So in order to do the frequency response analysis, here we will give a sinusoidal input signal. A sine wave is given as the input signal, and you will get an output across the capacitance, which is also a sinusoidal wave, sine wave, and there the amplitude and the phase of this output signal will be different from that of input signal. And in order to plot the frequency response characteristics, we need both magnitude as well as phase of the output signal. So we are again using a oscilloscope to obtain these quantities. So the input signal will be connected to one channel of the oscilloscope, and the output signal is connected to channel 2 of the oscilloscope. And in order to measure the phase difference between input signal and output signal, we can put the oscilloscope in XY mode. Then we will get a Lysage's pattern, and we will see how to measure the phase angle from the Lysage's pattern. Then the amplitude of the input signal and output signal can be directly observed from the oscilloscope. Okay, so here we are using sinusoidal signal for obtaining the frequency response. Previously we were using a square wave for getting the step response. Now we are using sinusoidal signal, and we will vary the frequency from very low value, say 100 Hz, to high frequency range, say 100 kHz, and we will observe the magnitude and the phase of the output signal when the frequency changes throughout this range. So here you can see the input signal. So a sinusoidal input is given, and the channel 1 is used to get the plot of input signal. Input signal is connected to channel 1, and it is 0.5 volt per division is the setting here. So one division will be 0.5 volt. So it is a 1 volt peak, sinusoidal signal of 1 volt peak. Then in channel 2 we are connecting the output signal, and if you observe the channel 2 waveform, you can see the output signal. It is also a sine wave, but there will be some phase shift, and there is a slight reduction in the amplitude. And if you change the frequency from say 1 kHz to higher values, when I increase the frequency, you can observe that the amplitude is decreasing, and there will be some phase shift between the two waveforms. And in order to measure the phase shift between the two signals, you have to put the two volt per divisions in the same value. Here we are using 0.5 volt per division in both the channels, and both the channels are connected in direct coupling. So now we will use this XY mode to observe the phase difference between the signals. So when I press the XY mode, a Lissajous pattern is obtained here. So from the Lissajous pattern, you can observe the you can calculate the phase difference. So the points to be measured are this length from the center of this plot to this intercept. This intercept is what you have to measure, that is one quantity. Then second number is you have to measure the height of this height difference between this edge and this reference. So I will show it in this here. So if this is the Lissajous pattern, we are giving the input signal to channel 1 and output signal to channel 2. Then you have to measure this height, say that is B, and you have to measure this value also, that is A. Then in order to get the phase difference between input and output, calculate sine inverse of B by A. So B is this Y intercept, and A is the height of this edge from the reference x-axis. Okay, from that you can calculate phase difference. So here if you change the frequency of the input signal, you can observe that the plot is Lissajous pattern is changing, and for higher frequencies the value will approach 90 degree. Okay, the phase difference will approach 90 degree. So by changing the frequency, you can you can calculate the value of phi, or phase angle. And in order to calculate the magnitude of input and output signal, you need to remove this XY mode, and you can directly observe the amplitude of input will not change because that is fixed, and the amplitude of output you can see here. So now at 8 kilohertz here, now the frequency is 8 kilohertz. At higher frequencies, amplitude of the output has reduced to lower values. If you reduce the frequency, you can see that amplitude is increasing. So you have to conduct this experiment for frequencies from lower values, say 100 Hz, to high frequency, say 100 kilohertz. You have to plot, tabulate both magnitude of input signal, magnitude of output signal, and the phase angle. Okay, so from that tabulation you can plot the frequency response, that is both magnitude plot and the phase plot of this particular first order system.